Hi everyone, my name is Aditya Anupam. I am a PhD student in digital media at Georgia Tech. I helped make the simulation engine, and this is a short tutorial on how to use our simulation engine when making games or interactive simulations about the COVID pandemic. Before we get into the code, I'd like to briefly describe the epidemiological model at the heart of the engine. The model that the engine uses is called the SIR model. This SIR model aims to predict changes in the fraction of susceptible S, infected I, and recovered people R in a given population. To do this, it draws upon the initial values of these three fractions along with the infection rate beta and the recovery rate gamma, which is just 1 upon the time of recovery, to solve three differential equations, one each for the S, I, and R fractions. So basically, all the engine is a differential equation solver that allows the user to change the initial conditions, and it outputs how the SIR values evolve based on those initial conditions. Now let's take a look at the files in the engine. I recommend you download the engine again even if you already have it, since I've rearranged some of the code. When you download the engine from GitHub, you'll have a zip file, and once you extract that, you'll have these 4 files in one folder. The readme.md file goes into more details about the SIR model and is a good reference to have if you forget something. The SIR model bundle file contains the main differential equation solver and the main helper functions to use the model. The example.js file contains a short example that demonstrates how to use the SIR model using the functions in the bundle. And the index.html file just displays the example on a web page console. Now, the folder is irrelevant for this demo as it basically contains instructions on how to make a multiplayer game using Node.js. For this tutorial, open up the index.html file, the example.js file, and the SIR model bundle file in your favorite code editor and navigate to the SIR model bundle file. Go to line 800 as that's where the code really begins. Everything above that is just code for the dependencies needed to solve the differential equations. Now I'll briefly explain the key functions of this file and then we'll move on to the example file. Lines 800 to 808 have a function called cityparams, which sets up the initial conditions or parameters for a given city. That includes beta, which is the infection rate, gamma, the recovery rate, S naught, the initial fraction of people who were susceptible to COVID, I naught, the initial fraction of people who were infected, and it uses those two to calculate the initial number of people who have recovered or are otherwise not susceptible to the virus. The functions from lines 811 to 828 sets up the three differential equations using beta and gamma. Next, we have the functions from lines 832 to 849, which is called SIR model, and this function basically solves the three differential equations using the initial conditions as input for a given number of days and shifts per day. Now, a simulation has to have an endpoint and a fixed time interval to do calculations for, and that's what the number of days and shifts per day do. We'll revisit them again in the example. The output of this function is a two-dimensional array, total number of shifts by 3, one each for S, I, and R, which outputs the SIR values for each shift for the given number of days. This array therefore contains the solution set output by the model and will be referred to as a city's disease model henceforth in the code. The next two functions are perhaps the most important functions. From lines 860 to 867, you have a function called infection prob city, which calculates the probability of getting infected given a city's disease model, or the SIR array calculated above, the given day, the given shift on the day, the total number of people there with that person, the probability of coming in contact with an infected person, and the probability that that contact is infectious and transmits the disease. Now, the latter three variables are what you can really play with in your game and simulation. If the total number of infected people with you in a location goes up, then your chances of infection go up. The function calculates the total number of infected people with you using the results of the SIR model calculated above, particularly the I value on a given shift and day. So for example, if the I value is 0.4 on a given day and shift, then you have a 40% chance that a person in a location with you is going to be infected. You multiply this with the total number of people there with you, say 10 people, and you can expect about 4 of them to be infected. If the location is small, like a small grocery store, then the probability that you will run into an infected person, the contact prob, goes up. So you can play with that. And finally, if the person sneezes a lot or doesn't wear a mask, then the chance of transmitting the infection to you or the infectious contact probe also goes up. So you can really play with these three parameters based on your game and simulation design. The other important function from lines 876 to 888 is called infection probe local, and it's really quite similar. The only difference is that it assumes you already know the number of sick people at a location beforehand. So it doesn't require you to have done any SIR calculations, as those are only necessary to calculate the fraction and number of infected people. If you already know how many sick people are there with you, then you can just use that directly, along with the contact probability and the infectious contact probability to determine your chances of getting infected at a given location. Next, lines 892 to 900 is a function called isInfected, and it determines whether or not you get infected using your chances or probability of being infected. Finally, lines 904 to 907 let you view the SIR values for a given day and shift. Now that's a lot to take in, so let's look at this in action in the example. So open up the example.js file. Here, from lines 7 to 12, I basically define the initial conditions. The transmission or infection rate, the recovery rate, which is basically 1 upon the number of days needed to recover, which on average is about 14 days or 2 weeks. So 1 upon 14. The initial fraction of susceptible people I've set as around 0.93 or 93%, and the initial fraction of infected people I've kept at 0.06 or 6%. And these values are drawn from when the pandemic began to peak in New York, but you can totally play with them or any other of the other parameters and see what happens. Next, I want to run the simulation for 21 days, and I assume 2 shifts per day, morning and afternoon. I shall set up these conditions using the city params function and I assign them to a variable called New York params. Now, to use any of the functions from the bundle file, such as city params, you have to prefix SIR model dot before the function name. So it's SIR model dot city params. Then I plug in these conditions along with the total days and shifts I want to run the simulation for, which is 21 days and 2 shifts per day, into the SIR model function. Again, I write that as SIR model dot SIR model here. This function then calculates all the SIR values calculated for each day, each shift and day for 21 days and 2 shifts, which I store in an array called New York SIR data. Now that we have all the SIR values for the 21 days, I can play around with that data. So for example, I can calculate my chances of getting infected on day 20, shift 1 at a location which has 30 people, where I have a 30% chance of running into an infected person and a 5% chance of that contact being infectious. These values can all vary based on the specifics of the location. So in a bigger location, you may have a lower chance of running into an infected person. So using the SIR data, this infection probe city function will calculate how many sick people are there and then use that along with all this other information, probabilities, to give me my chances of being infected. And I store that in a variable called infection probe. I can then plug in that probability in the isInfected function and I will know if I got infected or not this turn. So say my chances of getting infected were 40%, I plug that into the isInfected function and I have a 40% chance of getting infected. And I can also see the SIR values on a given day using the current SIR data function. Now just to compare, at the bottom I have all of these calculations done again, but this time I already know how many sick people are there with me in that location, and in this case it's 15 sick people. So I just use that infection probe local function directly instead to calculate my chances of infection. Now I've displayed all of these things in the index.html file. So open that up in your browser and then open the console. To open the console on a Mac, if you on the Chrome browser, you can go to View, Developer, and JavaScript console. Other browsers should also have a similar procedure. If not, just Google it. In the console, you will see 2 pieces of information: the probability of getting infected and whether or not you actually got infected for a situation. The one with 30 total people and the other where I knew 15 people were sick beforehand. And each time you refresh the page, you'll get a different result for whether you were infected or not. So right now, the location with 30 people on day 20 has 12 sick people and the chances of infection are around 19%. And here the player did not get infected. And on the other one with 15 sick people, your chances of infection is around 22% and you did get infected. Now, if I refresh the page, this will change. So that's it, folks. A full description of the code behind the simulation engine and an example of how it works and how to use it. Good luck.